Okay guys, welcome back. On this particular video, I will be covering a previous paper, February-March 2016. I'll be looking at question number 7, and that's actually based on acids and bases. Now, while I'm answering this question, I would like for you guys to pay attention to specific components that I'll be engaging in terms of answering this question, and what is it that I want you guys to take out from this, or take away from this. Now, as I go through the question, I'll be mentioning some things that are outside the question. However, those things will be necessary in order to fill in those gaps that are missing when approaching any chemistry question. Now, we need to have a thorough understanding of what's involved as far as this question is involved. Now, I'll take the first question. That's going to be 7.1. And I will be annotating for you guys on the screen to be able to see what I'm doing. All right. The first question wants you to define an acid in terms of Lawrence-Brewster theory. Remember, we have two acid-base models. The first one is Arrhenius acid base, and the second one is Lawrence-Brewster theory. Now, you should be able to know and state both of them. Use both of them actually for both acids and bases. All right, because they are asked just like that. All right, for the specific one, they want us to define Lawrence-Brewster space acid actually. Now, the acid, according to Brewster-Lowry, is a proton donor. Or in simple terms, you can just simply write an H plus donor, because the proton is the H plus ion. 7.2, carbonated water is an aqueous solution of carbonic acid, which is that formula. And carbonic acid, which is aqueous, ionizes in 2 steps when dissolved in water. All right. The reason being is because carbonic acid, just like sulfuric acid, they are both diprotic acids. The reason is they have the ability to donate 2 protons. That's why they undergo 2 steps of ionizations when dissolved in water, because they have 2 H's in their formula. I think you can recognize that, and the sulfuric acid that I've mentioned. They're those. So the diprotic acid. We also have triprotic acid, but we don't really touch on them that much. 7.2.1, they want you to write the formula of the conjugate base of the carbonic acid solution. Now, in order to do that, I think we should just do what I said in terms of showing the steps, the 2 steps of the ionizations, the ionization of the diprotic carbonic acid. So the first step should be H2 actually, CO3 plus, I'm gonna react that with water. If I react with water, I'm gonna get the carbonic acid is gonna dissociate into H plus and HCO3. So if it dissociates into H plus and HCO3, the H plus here is going to be donated to the water. In this case, the water will be acting as a base. Now, that's going to give me the hydronium ion plus, because I'm going to have to add this H into that. If I do add that H into this, I'm going to have 3 of them. And then the hydrogen here, ion with the proton, is a positive charge. And then the overall substance here will have a positive. And then I will remain with this. This is a -1 charge, since I've taken a +1 charge. Remember, the charge here was 0. So if I take 1 proton, which was positive, I'll be left with a negative. So it's going to be an HCO3 minus. Now the second step of ionization, would be to take the HCO3 minus, which is the hydrogen carbonate, and react it further with water. That's when the second hydrogen is going to come off, because we're going to have H plus and carbonate ion. The H again, same story, will be donated to the water, and I'll be left with this. And there we go. Now, so these are the two steps of ionization. So first, this was ionized into that, and the second step, this was ionized into that, and whatever there is there. All right. Okay, so what I want you guys to pay attention to is the equation they're gonna ask us next would be to write down the formula for the conjugate. Right? I want you to write down the formula for the conjugate, acid base of carbonic acid. So if we're going to write down the formula for the conjugated acid base, what I would like for you to do is just to look for something which is identical on the left-hand side, almost identical, not identical exactly, but which would look similar. I think similar is the word I'm looking for, which would look similar on the left and the right-hand side of the equation, except for the variation of charge. They may differ in charge, and then that's due to the difference in their H ion, or the H plus ion. Now, they look similar, but they have a different of H, which causes them to have a different of charge. So I've already showed you guys this, and this is basically similar, but they have a difference of an H, which gives them a different of a charge. So those are conjugate acid base. That's how you suppose them. So I'm gonna have H2CO3. They are looking for me to find the conjugate base of it. That's the one. They don't want me to write the two formulas. Actually, one will be enough. CO3 minus, that's going to be 7.2.1. On 7.2.2, they want me to write down the balance equation for the first step of ionization. And that's good because I've already did that there. So I'm just going to just copy and paste that. H2CO3 minus plus H2O. And then it's going to give me a hydrogen ion and hydrogen carbonate. Just fix my scene. Hydrogen carbonate ion, there we go. Now, to balance, obviously they usually come across balance. Okay, so we have 2 hydrogen and 2, which is going to give us a total of 4, and with 3 and 1, he was going to give us the total of 4. For the carbon, we have 1 here, and we also have 1 in the hydrogen carbonate ion, and oxygen we have 3 here, and we have 4, and we have 1 here, and then we have 3 here, which gives us the total of that. For the charges, we have a -1 here, and here we have a -1. We have a -1, and here we have a plus and a minus, which gives us a total of 0. Oh, we have no charge here. Excuse me. All right, we have a plus and a minus here. We get a total of 0 charge. Accidentally placed the charge here. I think it's because I saw this on top. All right, that will be it. All right, let's take a look at the next question. Though should be 7.3, I believe. 7.2.3 rather. There we go. All right. We're being told that the pH of a carbonic acid solution at 25 degrees Celsius is 3.4. I'm just going to head up and write that down. The pH of carbonic solution is 3.4 at 25 degrees Celsius. 25 degrees Celsius is the same as 298 Kelvin, if you want to use Kelvin temperature. All right, so they want you to calculate the hydroxide solution, the hydroxide ion concentration in the solution. So I think in order to do these, you're gonna have to think about what we've learned in terms of the ionization constant, and we have to use the pH since we're given the pH there. All right. Remember, the pH of a solution is going to be given by the negative logarithm the concentration of H plus ion. Now, sometimes you can write negative logarithm of the hydronium ion concentration. That should also be fine. As a matter of fact, they're used interchangeably. All right, because the concentration of the hydronium ion is due to the concentration of hydrogen ion of an acid. Since an acid is a proton donor. All right, whichever way you're comfortable with this. All right, so we're given the concentration as 3.4. So I think before we do that, we have to frame the concept of the equation. What is it that they actually are looking for as far as this question is involved? I think for the most part, they are looking for me to find the concentration of hydronium ion. Then if they're looking for that, I'll need to find on which equation that is. All right. There are two equations that will satisfy that. The first one is the ionization constant equation. The ionization constant equation, we have the concentration of H plus ion multiplied by the concentration of hydroxide ion should equals 1 multiplied by 10 or 1.0 multiplied by 10 to the power negative 14. That number has no unit. It's just the constant 1 multiplied by 10 or 1.0 by 10 to the negative 14. Another equation should be where I add the concentration, the pH of the hydroxide ion and plus the pH of the hydrogen ion. So I have the pOH, and then the pH, and that should give me 14. So these are the equations that can actually work for me. I'm going to try and utilize them both and see if I get the same or different answer. So let's first utilize this one. In order to use this one, I would need to get this. And then I'll have to solve this because it's equal to that. And then this will become the unknown, the concentration of the hydroxide ion will become the unknown value in this case. And I should be able to calculate that given I have the concentration of the hydrogen ion. Now, the concentration of the hydrogen ion I'm given here. All right, and remember this takes place at 25 degrees Celsius, and which is in line with what we've just said here. So we can go on and use this because it's at the same temperature parameters. All right. So I need to first get the pH, which is that, and then that will give me the H plus concentration. So let me use that equation. pH is a negative logarithm of H plus concentration. So the pH is 3.4. That's going to be a negative log of concentration of H plus ion. Now I will have to divide both sides of the equation with a negative. I don't want the logarithm to be negative before I take it off using exponential laws. That's going to be 3.4 equals logarithm of the concentration of H plus ion. Now the natural log is the base 10. So I simply would put the base 10 to the power 3.4 equals the concentration of H plus ion. We'll learn these guys in the experiment because logarithms are the inverse of exponents. Let's say, for example, you wanted to solve for x. Let's say 2 to the power x equals 4. And what I want is the exponent x. What I will do will be to just basically write this as an exponent of 2 to the power 2. So 2 to the x should be 2 to the power 2. And in this case, I will drop the exponent for x equals 2 since the bases are the same. However, I could do it in a different method. And that method will be to use logs. So let's say we have 2 to the x equals 4. Now I'll have to take the x and put it down and put the log of 2 equals the log of 4. So I will have to put the log both sides of the equation, having dropped that down. All right. So if I drop this down to be that coefficient, that's what I'm gonna have. So in that way, I'm gonna have x is equals to log 4 to the base of 2, or log 4 divided by log 2 if you want, which is the same as log 4 to the base of 2. Log 4 to the base of 2, this can be written as 2 to the power 2, which is 2 log 4, 2 log 2, excuse me, divided by log 2, or 2 log 2 base 2, if you may. And log 2 base 2 will cancel, and the remainder will be a 2. That's what I utilized here. So I just basically worked it reverse, if you may. So this 2 graph to the exponent x, and then I can get rid of that. I will be there. Here. Excuse me. All right. Let's go ahead and utilize the second method that I've used there. All right, so that's going to be 10 to the power negative 3.4. That's to give me that. So I've utilized that log in reverse. As we've seen, we can solve exponents using logs. We can use exponents to solve logs. If you have log of x base 2 is equals to 4, then x should be 2 to the power 4, which x is equals to 16. So, like I said, I've used that in reverse. You can use it forward and in reverse. All right, so what I'm going to have here is 10 to the power 3, negative 3.4. Ten to the power negative 3.4, which is the concentration of the hydrogen ion of 0.00398. I think after an 8 comes a 1. I don't have to do anything to that. All right, and then I can use the scientific notations, by the way, which is more simpler. And the scientific is 3.9. So the concentration of H plus ion should be 3.98 by 10 to the negative 4. Again, after an 8 comes a 1. I can round it to that. All right, mole per cubic decimeter. So that's the concentration of the hydrogen ion. Now that I have the concentration of the hydrogen ion, I can again use the Kw ionization constant for water. Now we know that the concentration of H plus ion multiplied by the concentration of OH minus, it should give me 1 multiplied by 10 to the negative 14 at 25 degrees Celsius, or simply at 298 kelvins. Now I'm going to have to take the H plus ion, since I do have it, and substitute for there, which is 3.98 multiplied by 10 to the power negative 4. And then I'm going to multiply that by the concentration of OH minus, which is 1 multiplied by 10 to the negative 4. I'm going to have to divide both sides by 3.98 multiplied by 10 to the exponent of 4. 3.98 by 10 to the exponent negative 4. Now I have the concentration of hydroxide ion, which is, I'm going to need the calculator for that. I'm going to go ahead and close that. So that's going to be 1 multiplied by 10 to the, 1 multiplied by 10 to the exponent of a negative 14. Dividing everything by, by 10 to the exponent of negative 14. And then I'm going to divide by 3.98 by 10 to the negative 4. So make sure that your exponents negatives are typed correctly. That's 25.125. There's some digit numbers. After that, multiply by 10 to the negative 20. I'd also have to utilize the exponential, the scientific notation, which is 2.51, 2.512. So I'm going to round 2.51 by 10 to the exponent of negative, I think it's to the exponent of negative 19. The exponent of negative 19, that will be the concentration of that. So that mole per cubic decimeter. So the concentration of that will be 2.51 multiplied by 10 to the negative 19. Now I do have the concentration of the hydroxide solution. Yeah. And again, I did say that another way you can utilize or get that answer is to utilize this equation actually, which is the P of OH and the P of H is gonna equals a 14. So POH plus pH equals 14. I do have the pH which is 3.4. It's equals to 14. So the POH is going to be a 14. I'm going to have to subtract 3.4 from 14. So if I subtract from 14 3.4, I'm going to get a 10.6. 10.6. So the 10.6 is the POH. But I know the POH, just like the pH is a negative logarithm of the concentration of H plus ion. The POH is the negative logarithm of the concentration of OH minus ion, just like that. Well, the pH measures the acidity scale. The POH will measure the alkalinity or basicity scale. So here I'm going to have this number here. That's 10.6 equals the negative log concentration of OH minus ion. Now the same thing will go as we did. So this is going to be negative 10.6 equals logarithm of concentration of OH minus ion. Now 10 to the exponent of a negative 10.6 is going to equal the concentration of OH minus, using the laws of exponents and logs. Well, then the concentration of OH minus ion, I'm going to write it there, is going to be 10 to the power negative 10.6. We should get the same answer as we did here for the 25.12 that which was 2.51 by 10 to the negative 19. All right, so I'm going to have 10, excuse me. I'm going to have 10 to the exponent, negative. It's going to be 10.6. And we do get the same number. Okay, so I'm going to have 2.51 multiplied by 10 to the power 19 mole per cubic decimeter. Now that's the concentration of that. Let's move on to the next question. In 7.3 or in 7.3, I'm going to have to take the rest of this to frame it contextually. All right, because if I miss some things about the questions, I might make some mistakes. Or we have X is a monoprotic acid. All right, so let's start with X as a monoprotic acid. State the meaning of the term monoprotic. A monoprotic, that's like I defined the diprotic here on top. The monoprotic is going to be, the word mono actually means one. The prefix mono there means one. The protic is just basically the proton. So a monoprotic is to donate one proton, or it's basically an acid that can donate one proton, or an acid with one proton. Okay, or one proton, an acid with one proton, acid containing one proton. Now we do know the acid containing one protons basically mostly is hydrochloric acid, nitric acid. Another one I think most acid actually, the hydrogen bromide, um, hydrogen chloride, a type of acid, they do contain that, but particularly we mostly deal with the hydrochloric acid on acid and base topic and nitric acid as well. Okay, so a sample of acid X is titrated. Remember, acid X is a monoprotic acid. It's titrated with a standard sodium hydroxide solution using a suitable indicator. And the question reads, at the end point, now the end point is, or the end point of a titration, is where it's where the neutralization reaction, obviously this takes place under neutralization reaction, where the acid and base which were neutralizing one each other have reacted on equal amounts. All right, so that's basically what the end point is. All right, so it's found that 25 cubic centimeter of X, which is the unknown acid X, and we know that the unknown acid X is monoprotic. So they're sort of giving us a hair start in terms of what is it that we should look for as far as this question is concerned. And so we should also pay attention to what are monoprotic acids and how do they actually behave. And what do we know of the monoprotic acid that we learned about for this particular topic? All right, so at the end, it is found that 25 cubic centimeter of the monoprotic acid X is neutralized by 27 actually 0.5 cubic centimeter of the sodium hydroxide concentration of 0. So this is a neutralization reaction. This could be taking on place between the hydrochloric acid and, hypothetically, the hydrochloric acid and the sodium hydroxide, between a strong acid and a strong base, I think, in my opinion, because most of these monoprotic acid are strong acid. Actually, the ones that we do learn about, the hydrochloric acid is, I think, is strong acid. I'm not quite sure about the nitric acid. I don't wanna make mistakes. Okay, so they want us to calculate the concentration of X. All right, so let's hypothetically think X is HCl, and then plus sodium hydroxide. We will get in this reaction the sodium chloride plus water. Remember, the neutralization reaction between an acid and a base give us salt and water. So now we have the salt of sodium chloride and the water molecule. So they want us to calculate the concentration of the acid X. So in order to find the concentration of the acid X, we need to find the number of mole of the, actually I think there are also two ways to do this thing. We have to find the number of moles of this one and use stoichiometry. Most acid-base neutralization reaction have the mole ratio 1:1. For monoprotic acid. For diprotic acid, it will be something else. All right. So what I'm going to do is to find the number of mole of sodium hydroxide. So the number of mole of sodium hydroxide will be its concentration times its volume. So let's find the concentration of sodium hydroxide and what will be the volume of sodium hydroxide. The concentration of sodium hydroxide is 0.1 mole per cubic decimeter, and the volume is 27.5 because this is for the acid X. So it's 27.5 cubic centimeter, which is 0.0275 cubic decimeter. You just simply take this number, 27.5, when divided by 1,000. So 27.5 divided by 1,000, we get a 0.0275. And then for the concentration of the acid, which is the acid X, is what we're looking for. The volume of the acid X, however, is 25 cubic decimeter, which is 0.025, again dividing by by, it's 25 cubic centimeter, which is 0.025 cubic decimeter, dividing that by 1,000, just like we did here. All right, so I'm looking for the number of moles of sodium hydroxide will be the concentration of sodium hydroxide, which is 0.1 mole per cubic decimeter, multiplied by the volume is 0.0275. Just move this a little bit. So 0.0275 cubic decimeter. Per cubic decimeters and cubic decimeters will cancel. So I have 0.1 multiplied by 0.025. 275 actually. That's going to be 0.00275 more. All right, and I'm going to have to use stoichiometry to compare the two to do that. So the number of mole of the sodium hydroxide to the number of mole of the acid X. Remember, the acid X is the monoprotic acid, and the monoprotic acid to the base, especially this base, will be more ratio 1:1, meaning that the number of mole of the acid X is going to be 0.00275 mole, equal to that one. All right. So we have the reacting and equal mole ratio, since they have 1:1 mole ratio, meaning that if I have the number of mole of the base, that will give me this exact number of mole for the acid X in this case. Right. Now remember, acid X is unknown. I just used hydrochloric acid just to frame the questions in a sense that you guys will be able to understand this. But you shouldn't write hydrochloric acid when solving. Like, I use acid X here, and I also use acid X there. All right, so the next thing would be for you to find this concentration. So its concentration of X will be the number of moles divided by volume. Number of moles 0.00275. The volume will be 25, which is 0.025, excuse me, 25 cubic decimeter. And that should give you, so here I'm gonna have to take the answer and divide by 0.025. So I'm gonna get a 0.11 or 0.1 mole per cubic decimeter. If you write 0.11 or 0.1, that should do it. All right. Okay, that's how you get your number of actually your concentration after getting the number of moles. So we have the concentration of acid X, or you could use the dilution equation of the concentration of acid times the volume of acid divided by the concentration of base times the volume of base will be the balancing coefficient of an acid divided by the balancing coefficient of base. N of A and N of B, those are a balancing coefficient. And I did say that it's 1:1, meaning that the concentration of acid multiplied by the volume of acid should equal the concentration of base multiplied by the volume of base, since this 1:1. If I do cross multiply, I'm still gonna get it. Concentration of acid is what I'm looking for. The volume is 0.025 cubic decimeter. The concentration of the base, I do have it, the concentration of sodium hydroxide, that is said to be 0.1 mole. So I have 0.1 mole per cubic decimeter. Multiplied by the volume is 0.0275 cubic decimeter. Cubic decimeter per cubic decimeter cancel. And I'm going to have to divide both sides by 0.025 cubic decimeter. Also divide the by 0.025 cubic decimeter. That should also work given the use of the equation. So we have the concentration of that multiplied by the volume of that. I'm betting we should get the same answer. Let's just use our calculator and see. So on the numerator, I have 0.1 multiplied by 0.025. And then 0.00275, and then I'm going to divide that by 0.025, which is a 0.11 mole per cubic decimeter. So that's your concentration of the acid X. Let's take a look at the next question. Hopefully it will be the last question. Now, on question 7.3.3, the concentration of hydronium ion in a sample of acid X is 2.4. All right, so we have the concentration of hydronium ion in a sample of acid X, which is the acid that we dealt with previously, monoprotic acid, is 2.4 multiplied by 10 to the negative 4. So they are asking if X is weak or strong acid. Now, given the context of how I framed the question, I've used hydrochloric acid. But we could have nitric acid, which is not a strong acid. Hydrochloric actually is. I think nitric acid is a strong acid as well. But depending on these numbers they gave us, I think we should be able to understand what is it that they want. All right. So the concentration of acid X, they want to know if it's the concentration of hydronium ion is in a sample of acid X is there. So it's acid X weak or strong. According to what I've said earlier, the acid X should be a strong acid because I've used hydrochloric acid and nitric acid. Hydrochloric acid, nitric acid, sulfuric acid are both classified, all classified as strong acid. So my best guess will be this is a strong acid, but we should be able to use these numbers and see if it is a strong acid. And then they explain your answer referring to the equation in 7.3.2, the previous one. Remember, you've got the 0.11 mole per cubic decimeter. So that's the concentration of that, and it's a monoprotic. So it means that if I have this concentration, if I'm having a strong acid, all the protons are converted into the hydronium ion proton. All right, meaning that the concentration of H plus ions here in the acid X are converted into the concentration of H3O plus ion. Now, they basically have the same concentration, in a sense, all right? So, but I'm given that I have 2.4. So if I have 2.4 multiplied by 10 to the power of that, I would use the pH to be able to find where the pH lies. I think that would help me if I find the pH lying somewhere between, let's say somewhere between 0, obviously it's going to be greater than 0, it's not equals to 0, somewhere between 0 and 3, 5, somewhere there, into range of 3 to 3.5 to 4, somewhere there. If it lies in this range, in this, I can say range or interval, then I would have, in my understanding, I would have a strong acid. But let's see, this should be fine. A negative log of 2.4 multiplied by 10 to the power minus 4. So your pH is going to be, so we have a negative log. The base will be 10. No, I don't want the answer. So we have a negative log. The base should be 10. And I have 2.4 by 10 to the exponent of a negative 4. That's 3.6. That's 3.61. All right, so I think I'm within the range that I somehow predicted. As long as we don't get to 4 or 5, we're within the range of strong acids. All right, so it should be a strong acid. But they said I should explain my answer referring to, so my best guess were right, but they say I should explain my answer referring to the question in 7.2.2, to the answer in question 7.2.2. The answer is this. So I'm betting it's because I have a strong concentration of the acid X. I don't know. What is a strong concentration? How does a strong concentration look like? That's really interesting. How does a strong concentration look like? Because if I'm gonna use this, if I were to frame it like this, I would understand. Because I would have to use calculation to say that. So, but we do have a strong acid. We do have a strong acid. But my best guess to giving an explanation is I'm stuck between a rock and a scissor here. Because if I'm to refer to this, I have to know what I'm referring to. So I'm not just gonna say some mumbo jumbo words. All right. Let me leave this to you, and then you guys should be sure to just link me if you have any idea in terms of how we can answer that referring to, we can explain our answer referring to the answer in question 7.3.2. All right. Okay, with that being said, that will be it for this video. I hope you get the takeaway that you guys were looking for. Good luck with your studies.